Okay, today we're going to continue with our lesson on finding zeros, and today we're going to extend that to complex zeros and using the prime factorization model, etc., like we did the other day, last lesson. So if we have a polynomial that has real coefficients, then a plus bi then could be a zero of the function, and a minus bi also a zero of the function. We call these complex zeros. And remember, the I stands for imaginary numbers. It's complex because we have a real part, which is a, and an imaginary part, which is the bi, plus or minus bi. So just to recall, I is equal to the square root of -1. But those are going to be complex zeros, which means they will not cross the x-axis. They won't be x-intercepts. They're going to be complex zeros. Now, before we get into these zeros, understand that every pair of complex numbers will come, or every single complex number, will come with a pair, with a partner. So in other words, you could have 3 plus radical 3 and 3 minus radical 2. Those would be real zeros. However, they could be complex as well, 4 plus 5i and 4 minus 5i. And the reason they come in pairs is because of this, the discriminant, right there. You're going to have a plus or a minus. So that is why we have the pairs of conjugates. So on example 8, and we could go back, we're going to do example 6. So if you look at your notes, we skipped example 6 for that reason, because it's going to be a complex pair. We know that we have 4. So we know that there's going to be 4 zeros, or possibly. Well, no, there's going to be 4 zeros. So it looks like -1 and 1 could be. Now remember, we need to do the P and Q. So 36, we have 1, 2, 3, 4, 6, oh my goodness, 9, 12, and 18 as possible factors, and 36, sorry. Q, though, is just 1, the coefficient of x to the 4th. So these are all, P over Q, then, are all of these possible real zeros. Well, it looks like to me there's a real zero, 1 or -1, or maybe both. So let's go ahead and use our synthetic division. Oops, I forgot x cubed, didn't I? X cubed is a 0. 105, x is 0, and then -36. So let's start the process here. That's 1 times 1 is 1. Add 0, you get 1. 1 times 1 is 1. Add those together, you get 6. 1 times 6 is 0. Or 1 times 6 is 6. 0 plus 6 is 6. 1 times 6, ooh, -30. Well, maybe 1 and negative, oh, gee, many Christmas. That was a 2, wasn't it? Well, there you go. There's the problem. You're watching this going, what is he doing? Right? Yes, I'm wondering myself. Well, that gives me -22, so that didn't work either, did it? So it's not a 2. I don't know if this is going by, I'm not sure what this is going by. 1050 -36. Well, I guess we can try 3. Let's see. What do we come up with? 3, 9, 42. Nope, not even close. Well, we've got an issue, don't we? Could it be factorable? Could we factor this? X squared and x squared. let's see, 12 times 3, nope. 9 times 4, there we go. Plus 9 minus 4, there we go. That will give us, and then we can factor this. I guess it's easier to factor it. So it was 4, or no, it should have been 2. 2 and negative 2. X equal 2 and x equal negative 2. So why didn't 2 work? What did we do wrong here? Bring down 1. 1 times 2 is 2. 2 times 2 is 4. Oh, there's our problem. That's 9. That's 18. It was 2. Again, hopefully you caught my mistake. Well, at any rate, we know it's 2 and negative 2 because we could also factor it. But synthetically division, I should just stop the video and start over. We know it's 2 and negative 2, so that is correct. So we found the real zeros. But now we have the complex zeros, and we have x squared plus 9 equals 0. So x squared equals negative 9, and then we take the square root, and we're going to get complex zeros of plus or minus 3i. So there are our 4 zeros. We have 2 imaginary and 2 real. So let's go back to number 6 that we skipped the other day. Hopefully I do it better this job this time. So we have P is 1 and 2, Q 1, 2, 3, and 6. So P over Q is plus or minus 1, plus or minus 2, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6. 2 over 2 is 1, 2/3 is the only one I'm missing, I believe. Well, looking at this, it looks like we might have a 0 at 2. So let's check it out. Hopefully I do a better job than I did last time. Bring down the 6, that's 12. Negative 2, negative 4, negative 1, negative 2. Bingo, it checks. So x equal 2 is a 0. And then we got this other garbage going in there, don't we? So let's try negative 1. Is that a possibility? Yep. And I'm not sure that it is, but we'll try. Bring down the 6, that's negative 6. Negative 1, that's 2, that's 0. Negative 1 times 0 is 0. Nope, negative 1 doesn't work. So it's not negative 1. Unless I did it wrong. 5 plus negative 6 is negative 1. There, I did. I did do it wrong. That's negative 1, positive 1. It is a 0. There we go. Got to get my algebra, my arithmetic correct. Negative 1 times negative 1 is positive 1. Negative 2 plus 1 is negative 1. Negative 1 times negative 1 is 1. Negative 1 plus 1 is 0. So x equal negative 1 is a 0. So we have 2 of the 4. Now there's 2 more. And we're left with 6x squared minus 1x minus 1 equals 0. I don't think that's factorable. So we want to use the quadratic formula. Negative b plus or minus negative 1 squared, b squared minus 4 times a times c all over 2 times a. Okay, so that's going to be 1 plus or minus 1 plus 24 all over 12, I believe. Yes, 24. So that's going to be 1 plus or minus 25 square root of all over 12, or 1 plus or minus 5 over 12. So there's our 2 answers, 1 plus 5 divided by 12 and 1 minus 5 divided by 12. So 6/12 is 1/2, and negative 4/12 is negative 1/3. So see if those, yeah, that looks about right, and there's one of the answers. So there are our 4 zeros, and they're all real. Now, why did we hold off on that? Because we had to use the quadratic formula to find those two zeros right here. That was the only way to find them, which is what we're going to have to do on some of these conjugate pair type problems. Okay, so on the next one, P is 1, 2, and 4, and Q is simply 1. So it looks like it's going to be plus or minus 1, 2, and 4. And that looks like negative 2 is a 0. So we have a cubic, so we should have 3. So it looks like, but there's only 1, isn't there? So the other 2 have to be imaginary. So we have 1x cubed, 0x squared, negative 2x, and 4. So that's 1 times negative 2 is negative 2. Negative 2 times negative 2 is 4. That's 2. Negative 2 times 2 is negative 4. That's 0. So x equal negative 2 is a 0. So that leaves us with x squared minus 2x plus 2 equals 0, which the only way to solve that is to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2 times a. And the formula is back here. So you already wrote it down. We're just using it. So that's going to be 2 plus or minus 4 minus 8 over 2. And you can check my arithmetic, but I think this is right. So now I have 2 plus or minus radical negative 4 over 2, which, hey, this is going to be imaginary, which is 2i, isn't it? Square root of 4. So 2 plus or minus 2i over 2, which becomes 1 plus or minus I. So there's our 3 zeros. Here's 2 of them. Here's 1 of them. Real and 2 complex, which matches the graph. We only have 1 real, so we should have 2 complex. Okay, now the next one, were we supposed to write the linear factors? Nope, we're supposed to find the zeros. Here we're going to write the linear factors. So let's do our P and Q business. 1, 5, 7, and 35, I believe. And our Q is just 1, so these are all our zeros. 1, 2, 3, 4, 5. Looks like negative 5 must be the answer. Let's synthetically divide it in order to find the next. So that works, x equal negative 5. So now we have x squared plus 4x plus 7 equals 0. Does that factor? I do not believe so, plus I know it doesn't. So negative b plus or minus b squared minus 4ac all over 2a, which will be 16 minus 28 all over 2, okay, which is going to be negative 12. Now, negative 12 obviously is going to be an I, but 12 breaks down into 4 and 3, which is 2 radical 3, and we need an I, so that's going to be negative 4 plus or minus 2I radical 3. Always write the I after the whole number, or the real number in front, whatever you want to say, and then divide 2 in all those places. And I think there's your 2 complex. So now we're supposed to write this as a product of linear factors. Okay. So h of x equals, let's take this first one, x plus 5, x minus negative 2 plus or negative 2, that should be a plus or minus. Gotta get this straight here. So x minus, yes, it'll always be minus 2 minus I rad 3, double parentheses, and x minus negative 2 plus I rad 3. Now, you may have to simplify this. I don't think you do on your WebAssign, but we could just distribute the negative sign. So it's x plus 2 plus I rad 3, and this would be x plus 2 minus I rad 3 is what it ends up being. So there's your factors. So then when I write my equation for these with the following zeros, remember anytime we have an imaginary or a complex or a real with a radical, we're going to have multiple. So in other words, this is going to be x minus 4, x minus 3i, x minus negative 3i, which is plus 3i. This one would be x minus 2, x minus 4 minus I, and x minus 4 plus I. And again, if you're going to clean that up, it's going to be x minus 2, x minus 4 plus I, and x minus 4 minus I. For the last one, it's going to be x minus 2, x minus the quantity 3 minus 2 radical 2, and x minus 3 plus 2 radical 2, parentheses. And so you can clean that up if you choose to look like this or that.